Welcome to this video. In this video we will talk about voltage and current sources, and we'll cover basically what they are. We actually won't do many examples in this video. This is background information that hopefully you'll be able to refer to when you start working circuit analysis problems. So we'll start off by talking about a voltage source. And we typically have two schematic symbols for voltage sources. The first one you've seen if you've watched previous videos. It looks like this. And then you typically label it with a voltage, say 3 volts. This represents a constant source. And the idea is that the 3 volts here that the source puts out doesn't change. The origin of this symbol is the parallel plates that often, or at least used to show up in batteries that when the symbols were put together were often made of parallel plates immersed in an electrolyte, some sort of liquid. So we use this for a constant source. Another symbol that you'll see quite often is a circle with a plus and minus in it, and you'll see something like V sub S, or perhaps some constant voltage, say maybe something like 2 volts or whatever. But the idea is that this is also a voltage source, but it's possibly time varying. In other words, V sub S might be some signal that changes as a function of time. So for example, V sub S could be something like 10 cosine 377t. Okay, just as an example. In other words, the big difference here between this symbol and this symbol is the fact that the second symbol, the circle, could represent a time-varying voltage. Okay. Now, when we do circuit analysis, we'll typically assume that our sources, both voltage and current sources, are ideal. And an ideal voltage source will provide any current needed. And the idea is that, for example, if I go back to our light bulb example that we've used in previous videos, and suppose I have a 3 volt source here and I have a light bulb. This 3 volt source will provide whatever current is needed to this light bulb to make sure that the voltage stays at 3 volts. So no matter what size light bulb I have, say for example the light bulb we've been talking about is about a 1.4 watt light bulb. If I were to replace that 1.4 watt light bulb with a billion watt light bulb, this voltage source would increase the current necessary to be able to provide a power of 1 billion watts at 3 volts. Now, in real life, that doesn't happen. There's no way I'm going to have a battery that's able to supply 1 billion watts. Okay, so that's the difference between an ideal source and a real source. Real voltage sources include batteries, generators, both AC and DC. If you live in a house where you have electric power, quite often you'll think of the wall outlet as an ideal voltage sources. And as a voltage source, real sources are not ideal. Typically, the current tends to drop as the voltage supplied by the source tends to drop as you increase the current. So again, if you've for example, got a battery, there's no way it's going to provide you 1 billion watts. And so to represent a real source, typically what you'll see is an ideal voltage source that also has a resistor connected to it in this way. And in later videos, we'll come back and actually explore what this means. But the idea is this R sub S represents the internal resistance of a battery or something like that. Okay, but for circuit analysis purposes, again, the important concept to remember is that an ideal voltage source will provide any current that you need in order to keep the voltage at what you want it to be. So we'll clear this, and now we'll talk a little bit about a current source. Current sources are represented by a circle with an arrow in it, and I might label the current that's being provided by the source, for example, 1 amp, or I might have some I sub S. We typically don't make the distinction between constant and time-varying current sources. Now, this current source will have a voltage across it, and the idea behind a current source, an ideal current source, is it will make the voltage whatever's necessary which I can't spell. It'll make the voltage whatever's necessary to have the current be 1 amp. So again, if I, for example, were to hook up a ideal current source to a 1 watt load, it would make the voltage necessary to provide 1 watt of power. If I were to hook up a current source to a 1 billion watt load, it would make the voltage whatever's necessary to provide 1 billion watts. Examples of real voltage sources in the real world are much less common than examples of real current sources are much less common than real voltage sources. In my experience, they typically tend to be used in the design of transistor circuits, where you need to have a constant current in order to make a transistor do something. Now, non-ideal sources, it turns out that just as I can represent a battery or some other non-ideal source as a voltage source connected to a resistor, I can represent a non-ideal current source as a current source connected in parallel to a resistor. Okay, and it turns out that this representation is mathematically equivalent to the representation that we had for the non-ideal voltage source. This is a particular instance of source transformation, which is a topic that we'll get to quite a bit later. Okay, one last topic and then we're done with this video. You'll notice that I've been representing current sources with circles. When I had voltage sources, I represented them with circles. The circle implies an independent source. And what that means is that the voltage or the current supplied by this source is independent of any other voltage or current supplied or anywhere else in the circuit, which sometimes is exactly what you want. When your source is providing the power to a circuit, you want it to stay the same voltage or the same current no matter what. But in some applications, particularly when you're modeling amplifiers or components that are used in amplifiers like transistors, you want to be able to have a source where the current or voltage across the source depends on some other current or voltage somewhere else in the circuit. And so to do that, we have what we call dependent sources. And so I have here the 4 types of dependent sources you can have, and you'll notice that every dependent source has a diamond shape in it. This basically is the part of the dependent source that actually provides the voltage or the current. So if we start looking at the voltage-controlled voltage source, what this means is that I look at some voltage somewhere in the circuit. In this case, I've denoted it as V sub x. My controlled source will give me some constant alpha times Vx as an output. So for example, when you're modeling an operational amplifier, which we'll do later, alpha might be 1,000, and so the output of this controlled source will be 1,000 times whatever V sub x is. And again, V sub x is some voltage somewhere in the circuit. Another type of controlled source is the voltage-controlled current source. Again, for the voltage-controlled current source, you monitor some voltage in the circuit. The source then provides some constant gamma times this voltage. This particular type of model is often used when you're dealing with transistor models. And the other 2 types of sources are similar. You have a current-controlled voltage source. So the idea here is you model or you monitor some current somewhere in the circuit, and the output of the source is a voltage that's proportional with this proportionality constant beta times the current. This turns out to be the model of a bipolar junction transistor. And so in fact, when you look at the spec sheet on a bipolar junction transistor, sometimes you'll actually see beta supplied there. And finally, to round things out, you have a current-controlled current source. So you monitor some current somewhere in the circuit, and the output of the source is sigma times that current. So again, the controlled source models are used primarily when you're dealing with amplifiers and transistor modeling and such. They're very useful there. They introduce some interesting complications into circuit analysis, which we'll talk about when we get to those sorts of circuits in later videos. So that concludes this video on sources. Thanks for watching. Hopefully this has been helpful.